Swayam Prabha. Digital India. Educated India.
Let us begin the discussion of lecture 52. Here we continue with our discussions on the hypersonic wind tunnel that we had discussed in the previous lecture. We will also try to extend the discussion to shock tube and shock tunnel, looking at the basic concepts. Last lecture had highlighted about supersonic and hypersonic wind tunnel, the basic concepts. We continue with some more interesting points about continuous flow hypersonic wind tunnels. The first point is that in some of the tunnels, the gas used is pure nitrogen instead of air. So, we would choose to use nitrogen as the working medium, and there are reasons behind it. Nitrogen has the same ratio of specific heats, namely 1.4 as air. However, it has a lower liquefaction temperature and hence can be expanded to higher Mach numbers and lower temperatures in the test section. This is a clear advantage over air, because we saw that under hypersonic Mach number conditions, liquefaction of the working medium happens to be a major issue. Therefore, nitrogen has a clear advantage over air. Different nozzles, which are often in the form of liners, are used to obtain a range of Mach numbers in these hypersonic tunnels, thereby giving some width to the Mach numbers which you achieve in the test section. The nozzles are connected to a fixed test section which can have certain length and diameter. Ideal hypersonic test facilities would simultaneously be able to simulate a certain Mach number, velocity, enthalpy as well as Reynolds number, which are typical of a particular flight condition in the atmosphere. However, simultaneously matching them is essentially an impossible task, and therefore, in any given facility maybe one or two conditions are fulfilled while others are sacrificed or compromised. Hypersonic wind tunnels deal with high supersonic Mach numbers, usually over a range. Practical advantage that you gain out of that range is that you might find that Mach number independence shows up through some of the non-dimensional coefficients that are generated through the test data. For example, pressure coefficient, lift coefficient, wave drag coefficient and so on may show some kind of a Mach number independence beyond a certain level of Mach number once reached. For some aerodynamic data, simulating the precise Mach number is not so important. As long as we have reached a condition where Mach number independence has been achieved, the specific value is not so important. While for certain others like skin friction or heat transfer coefficient or hypersonic viscous interactions, which we will discuss in a later lecture possibly, are all dependent on Reynolds number. Therefore, Mach number is not the only connection, Reynolds number also happens to be important. Therefore, apart from high temperature effects associated with high enthalpy levels, a hypersonic test facility will be very useful if it can simulate both Mach number and Reynolds number according to our need or expectation. Since Reynolds number by definition is rho VL by mu, a large size of test section length or large nozzle exit diameter would increase the characteristic dimension L. Large reservoir pressure serves to increase the density. Large reservoir pressure also increases V in general, Therefore, these factors, if we are able to increase as far as possible based on the cost constraints, would influence maximization of the available Reynolds number. However, increasing all these beyond a certain limit can be prohibitively costly, not only in terms of building and installation, but also running the tunnel will consume a huge amount of power, and therefore, scaling has to be very carefully done. An adequate range of test section Reynolds numbers helps the study of phenomena like transition from laminar to turbulent flow on the model surface, as well as turbulent skin friction and heat transfer, where we know from our prior experience that the turbulent quantities are usually greater, often much greater than the laminar counterparts. We are citing an example here with due regard to the source hypersonic and high temperature gas dynamics by J.D. Anderson, where we have looked at a plot for the heat transfer in megawatt per meter square along a certain region of the wing surface of the space shuttle. This is the span-wise location which has been chosen, and then along the span-wise location that is chosen, if you traverse from the leading edge towards the trailing edge, this is how you will see the laminar and the turbulent quantities varying. Therefore, there is a wide gap between the two. That is the main message that we are trying to discuss or point out at this juncture. Therefore, if you are able to simulate the correct conditions, whether it is laminar or transitional or fully turbulent, then you should be able to get a much better assessment of both skin friction as well as heat transfer coefficients, which is extremely important in studying hypersonic flows over practical vehicle configurations. For many aspects of flight through the atmosphere, velocity and not just Mach number is an important parameter. This we had in fact emphasized many times, that in hypersonic flow theory also we can show that Mach number loses significance. Instead, the velocity becomes the more pertinent parameter. In the type of cold flow hypersonic wind tunnel that we discussed earlier, the hypersonic Mach numbers in the test section are produced mainly due to the relatively low speed of sound associated with the cold free stream temperature rather than a high free stream velocity. So, the point that we are trying to make is that with the expansion of the flow to hypersonic conditions, the temperature usually drops quite significantly, and the sonic speed being root of gamma r t will correspondingly see significant drops, and based on that even high Mach numbers may not necessarily mean high velocities. Just to check with two cases, we are mentioning them as case A and case B, which we have been handling. We had done those calculations in the previous lecture. Air at 1 atm pressure with the liquefaction temperature of 81 Kelvin, if we take this as the case A and the case B as the standard altitude of 59 kilometers, temperature, atmospheric temperature being 256 Kelvin makes the case B, then at those two temperatures, if you try to work out the speed of sound, in the 81.6 Kelvin case, you find that the speed of sound comes out to be 56.6 meters per second, which is way smaller than what we are used to at standard sea level conditions, which is more than 300 meters per second. And based on this very small sonic speed, the velocity at Mach 10 comes out to be 566 meters per second, which would barely be about 1.5 or little more than that at sea level conditions in terms of Mach number. But just because the temperature has fallen to such low values, you see a significantly high Mach number being attained with 566 meters per second velocity. Remember that the corresponding T naught was about 1714 Kelvin. Now, going to case B, The speed of sound corresponding to 256 Kelvin would be 320.7 meters per second, and the corresponding flow velocity for the same Mach 10 condition will be way larger, 3207 meters per second. The corresponding T naught would be 5376 Kelvin, which we had discussed is a huge temperature to handle. So, we saw two cases where if the reference temperatures are significantly different, how it may influence the test section velocity. Now, when speeds greater than 3 kilometers per second are encountered, we generally classify them as hypervelocity. Clearly, the cold flow hypersonic wind, which just about prevents liquefaction of air as it expands, considered as case A in the previous slide, is not compatible with test section velocity requirement of a hypervelocity tunnel, while the case B is just about so. There is a dramatic difference in the stagnation pressure and stagnation temperature requirements for the two cases. We once again take note of them, this corresponding to A, while this corresponds to B. The advantage of simulating velocity in a wind tunnel is the resulting simulation of a dynamic pressure to be encountered by a hypersonic flight vehicle. So, we are talking about simulating the appropriate velocity. So, this is an appropriate velocity that we are talking about, and therefore, we are just assuring that dynamic pressure is well represented in the test section, and dynamic pressure has a direct connection with aerodynamic forces which are exerted on the aerodynamic surfaces of the vehicle, and therefore, it also has implications of structural integrity and flight trajectories. So, maintaining dynamic pressure is a very important requirement, and that is suitably met if you are maintaining the proper velocities in the test section, and therefore, having appropriate velocities connected with the practical application is so very important. Also, when you look at air breathing hypersonic vehicles, the dynamic pressure is an important factor in the engine performance, and therefore, if we are using engines like ramjets and scramjets, then we need to look at the dynamic pressure when we are looking at their performances. Till now, we discussed how Mach number is simulated in cold flow wind tunnels with air heated in the reservoir to the extent to avoid air liquefaction in the test section. That is the threadbare requirement. Moreover, the reservoir pressure can be made high enough and the size of the wind tunnel made large enough to simulate realistic Reynolds numbers. In the cold flow blow down hypersonic tunnels, high Mach numbers in the test sections are obtained by expanding the flow to lower temperatures through high area ratio nozzles. The higher Mach number is due to lower temperature of the gas in the test section, not necessarily due to marked higher flow velocity. So, these are some of the points we have already mentioned, we are recapitulating them, and we come to the conclusion that the only way to obtain higher velocities in the test facility is to have higher energy flow, that is to have more enthalpy dumped into the flow. So, we need high enthalpy or high temperature facilities, and one of the most popular and practical ways of doing it is through shock tubes. So, we come to the high enthalpy, high temperature facilities and their practical need, and we try discussing about the basics of shock tubes, how they are relevant to us in this context. The temperatures encountered in the stagnation regions of hypersonic re-entry vehicles, where it is atmospheric entry by a vehicle in Earth orbit, typically like the space shuttle, would give rise to stagnation temperatures of the order of about 7500 Kelvin, while if we are talking about a lunar return vehicle, then the stagnation region in the shock region or shock layer would immediately increase to few thousand Kelvin more, which is about 11,000 Kelvin. If it is a Mars space vehicle returning to Earth, then that will shoot up further to about 15,000 Kelvin. because of the differences in the accompanying velocities at which they re-enter. Further, it is to be noted that all the above mentioned temperature levels that we are talking about, they assume local chemical and thermodynamic equilibrium in the shock layer. Many of the above flows may encounter some portions of non-equilibrium flow, which is evident from some of our earlier discussions too, around typical bodies like block bodies or nozzle flows that we have discussed earlier. Non-equilibrium in the shock layer will result in even higher temperatures. So, this is a very, very important fact that we have to keep in mind, and we have to be very carefully avoiding non-equilibrium as far as possible. However, in certain conditions they are practically inevitable. With the current available state of the art high temperature withstanding materials to contain gases at these temperatures in pressure vessels for a reasonable time span is practically impossible, and therefore, storage for significant times and running the facilities for significant time spans is not the viable option. So, this is not a viable option, and therefore, we have to look for one, and the shock tubes essentially feed us that viability. The type of blow down hypersonic wind tunnel that we discussed in the previous slides will not work for high reservoir temperatures required to simulate Earth atmospheric entry of space vehicles, especially if it is getting to those kind of temperature ranges in terms of stagnation temperature that we just saw in the previous slide. The major challenge is that aerodynamic heat transfer problems encountered by hypersonic vehicles in flight translate to similar severe heat transfer problems faced in ground test facilities, which are meant to simulate them. And therefore, it is not only that those vehicles will encounter these kind of heat transfer problems, the ground test facilities also suffer from the same. The only way you can kind of avert this problem to a significant extent is to reduce the test times. So, the practical solution is to generate such temperatures for only very short periods of time, either in milliseconds or even microseconds. The strategy behind this is that even though the instantaneous heat transfer rates to the surface may be very large, the total amount of heat transfer which is integrated over the short period of time still remains rather small. This heat can be readily absorbed by the material heat withstanding material without impairing the structural integrity of the facility. And this is the major strategy shift or paradigm shift that we talk about, which brings about success in handling the high temperature conditions typical of the re-entry either from Earth orbit or from lunar missions or from missions to Mars and so on. So, these facilities which can handle such kind of situations, small test time, but create very high temperatures and test them for short durations etc., are called as impulse facilities. And the heart of that kind of facility is the shock tube. This is the most commonly and widely used facility variant. This device is a closed tube that initially has high pressure gas separated from low pressure gas by a diaphragm. So, this is like the central portion of the long metallic tube which is closed at two ends. You have the two sections divided by means of the diaphragm. You see one is at a much higher pressure than the other. It could be at a different temperature too. The pressure, temperature, viscosity coefficient, sonic speed, gamma etc. of the two media are highlighted. They are numbered like this 4 and 1 because there are states 2 and 3 which develop once the diaphragm is ruptured, and you see a clear cut step pressure difference between the two regions to begin with. And then once the diaphragm ruptures, you will see a distribution which looks more like this. We will try to discuss it in a while from now. So, let us come back to this and read the points that we have over here. The gas in the high pressure section, which we call as the driver section, is usually a different gas than in the low pressure section, which is called as the driven section. We purposely choose different gases because of some inherent reasons we will discuss soon. In the driver section, which is labeled as 4, pressure is P4, temperature T4, molecular weight of the gas is M4, speed of sound is A4, and specific heat ratio gamma 4. Similarly, you have the subscript 1 conditions in the driven section. When the diaphragm ruptures, a normal shock wave propagates into section 1 and an expansion shock or rather expansion wave propagates into section 4. The diaphragm can be ruptured by different means, either by use of a electrical current or some mechanical means. Now, we follow the different patterns which move into the two regions after the diaphragm ruptures. As the normal shock wave propagates to the right, it moves with a velocity w, that is how we indicate it. It increases the pressure and temperature of the gas behind it. We call this as the region 2 and induces a mass motion with velocity u p. So, it is good to have a look at it for a while. So, this is when the diaphragm has ruptured and you see a shock, a normal shock moving to the right with velocity w relative to the laboratory frame of reference. We had called these regions 1 and 4 in the beginning. Now, as you see, there are 2 more regions 2 and 3 which have opened up, and we have a contact surface which is the interface between the driver and driven gases. It moves to the right with velocity u p, which is an induced velocity basically, and that velocity is relative to the laboratory frame of reference. And on the other side, you have a movement of expansion wave propagating to the left, and you have the head and the tail of the expansion wave and the series of wave fronts indicated through the straight lines, a series of straight lines which we have represented there. Of course, this is an isentropic phenomena, and you see the variation of pressure in the different portions, P 1 in region 1, P 2 equal to P 3 in region 2. There is a step jump here because of the shock. There is a gradual change of pressure in this region because of the isentropic expansion, and therefore, the pressure variation now looks quite different. Coming back to this, the interface between the driver and driven gas, we saw it is the contact surface moving at u p. The expansion wave propagates to the left smoothly and continuously, decreasing the pressure in region 4 to the lower pressure P 3, and the moving high temperature gas behind the shock wave in region 2 can be used as a test medium. So, if you put a model in that region, possibly you can acquire some data out of that. The most important thing is that by virtue of the shock crossing that region, the temperature of the gas gets far elevated, and that is an advantage. For a sufficiently high diaphragm pressure ratio P 4 by P 1, the strength of the normal shock propagating through the driven gas can be sufficient, so that the u p becomes supersonic, and therefore, high temperature supersonic test conditions will actually be created in the wake of the shock. Incidentally, it can be shown that the Mach number u p by A 2 can at max become 1.89 if you assume the gas to be calorically perfect, though that is a highly simplified assumption, because as you know, under such very high temperature conditions it will become a reacting gas. That is the point coming up next, that when the shock wave is really strong, the flow behind it in region 2 is a high temperature, vibrationally excited, chemically reacting gas, and the above result for calorically perfect gas will be substantially modified. It will not be quantitatively accurate. However, the simplified theory based on calorically perfect gas still gives us some very important indications. The techniques taught in earlier lectures can be used to calculate the chemical composition and properties of such a gas mixture. So, this is what you should start thinking now, and that would give you good recapitulation too of some of the concepts that you have learnt in that relation. The advantage of using different gases in the driver and driven sections of a shock tube is shown by the following relation that we have between P 4 by P 1. This equation relates the strength of the incident shock wave P 2 by P 1 to the initial diaphragm pressure ratio P 4 by P 1. So, this is what we had before the diaphragm ruptured, while P 2 by P 1 is now basically the ratio between these two pressures, which is the ratio across the shock. For a calorically perfect gas, we can show that this is how the two pressure ratios connect. The above equation gives the incident shock strength P 2 by P 1 as an implicit function of the diaphragm pressure ratio. That is because in several places on the right hand side you can see P 2 by P 1 ratio, and therefore, it is not straightforward to obtain it. It has to be done in an iterative manner. An examination of this relation shows that for a given diaphragm pressure ratio, which is P 4 by P 1, the incident shock strength P 2 by P 1 will be made stronger as A 1 by A 4 is made smaller. So, we are trying to say that as this becomes smaller, the P 2 by P 1 ratio will be stronger, which means it will become larger. Now, from the definition of A, we know it is nothing but under root gamma R T, where this R is specific gas constant, while the other R is the universal gas constant with the molecular weight of the gas in the denominator. Based on the m in the denominator, we can easily see that speed of sound in a light gas is always faster than in a heavy gas. This gives a very valuable clue that to maximize the incident shock strength for a given P 4 by P 1, the driver gas should be a low molecular weight gas at high temperature. Hence, you will get high A 4, and the driver gas driven gas rather should be a high molecular weight gas at low temperature, hence low A 1. For this reason, many shock tubes in practice use hydrogen or helium for the driver gas, because they are very low molecular weight gases. However, handling hydrogen is quite hazardous, and thereby using helium, which is inert, could be safer. And then if you heat the driver gas by electrical means, say arc driven shock tube, or by chemical combustion, that means by using some fuel in that region and combusting it, raising the temperature of the driver gas, you can maximize the incident shock strength. We need to analyze what happens when the incident shock waves hit the end wall on the right. So, at some point the shock will go and meet the end wall here. At this instant, it appears that the flow will be directed into the wall, and if you think carefully, that is physically impossible, because the wall is a rigid one, and if it can withstand that pressure, it will not allow the shock to move through. Therefore, under such condition, the velocity normal to the surface must remain 0. Now, the mechanism that nature has devised to handle such a situation is that it reflects back the shock with a velocity of W r towards the left, and that leaves the region in the wake of the reflected shock stagnant, which means the region 5 now emerges after the shock has met the end wall and has reflected back, where the region 5 is essentially static relative to the laboratory. Although the gas behind the reflected shock has no velocity relative to the laboratory, the importance of it is that the temperature of that gas is greatly increased compared to that achieved in region 2 behind the incident shock. That is because this gas has been influenced by two shock waves successively. One is the incident shock, the other is the reflected shock, and therefore, there has been a twofold increase practically in its temperature. The value of this almost motionless region of gas at high temperature is enormous. So, that can be used for obtaining a spectrum of data. For example, the relaxation of the region immediately behind the reflected shock from frozen to equilibrium conditions provides data on chemical reaction rates. That is one possibility, and the measurement of heat transfer to the end wall provides data on both convective and radiative heat transfer to stagnation point of hypersonic vehicles. That is another important application. There is still more to it. Spectroscopic measurements of the radiation from this gas gives detailed information on the spectral emission from a high temperature gas. So, there are multiple applications of this. Further, it can be used for running a very important facility which is called as a shock tunnel, where we basically make use of this high temperature, high pressure gas to be subsequently expanded through a CD nozzle into a test section by means of a second diaphragm that we open up at the end wall. And therefore, instead of a rigid diaphragm which helps to reflect back the shock, we allow a second diaphragm, and then after the incident shock reflects from the end wall, forming a reservoir of hot high pressure gas in region 5, the second diaphragm is broken. This is evident from a sketch like this, where we can see that the end wall of the shock tube was lying over here, where we placed a second diaphragm, and then once the shock reflected back, we are going to rupture the second diaphragm. As a consequence, the high pressure, high temperature gas behind the reflected shock, which the reflected shock has left behind it, would now be expanded through a hypersonic nozzle, which is here, the throat of the nozzle is here, and you have a flow which moves towards the right through the test section, which is at an elevated temperature and pressure too, and then it moves into a dump tank. So, that is basically the mechanism that we have in a shock tunnel. Therefore, there is a tunnel we have over here which is run by a shock tube essentially. So, the rupture of the second diaphragm again can happen mechanically, electrically, or simply by large pressure difference between high pressure in region 5 behind the reflected shock and low pressure in the evacuated dump tank in region 7. And this facility can, for a short period of time, typically of the order of milliseconds, create a high enthalpy, high velocity flow in the test section. So, this is an enormous advantage that one can benefit out of. How long can this meaningfully operate? If we recall, after the primary diaphragm is broken, a shock wave propagates into region 1 with velocity w. However, at the same time an expansion wave propagates to the left. When this left running expansion wave hits the left hand wall of the shock tube, it will reflect as right running expansion wave. Because expansion waves have finite thickness and there will also be a mix of simple and non-simple wave regions, the reflected expansion wave will immediately interact with the left running incident expansion wave, resulting in a rather complex wave system that would enter into region 3 and continue to propagate to the right through the regions 3 and 2, while at the same time the reflected shock wave propagating to the left then encounters this complex right running expansion wave system, and thereby the uniformity of properties in the two distinct regions gets lost. This ends the uniformity of the expansion through the shock tunnel nozzle, and hence it ends the useful test time in the shock tunnel. So, we have to restrict the run time of the shock tunnel to the happening of the interaction of the reflected shock and the right running expansion wave family. Let us conclude by saying that in this lecture we discussed about some interesting points regarding hypersonic tunnels which were left from what we had discussed in the previous lecture. We further extended our thoughts to introduction of shock tube and shock tunnel. Thank you.